Hi, welcome back to the next video. In this video, we will talk about one more approach to modeling growth of bacterial cultures. So, just by way of recap, we have done exponential growth, which we found out that was extremely unrealistic because the numbers blew up very fast. In the last video, we talked about logistic growth, which we found was extremely successful at capturing different facets of growth in a batch culture. The near exponential growth, the slowing down phase, and finally growth approaching 0. This, however, this was a very useful model, but this was only approaching for this was only appropriate for a batch culture. And we want to discuss one more model for capturing growth dynamics of bacterial species, and after that we will be armed with these 3 different models, and depending on the context in which we are discussing results, we will be able to bring these models back into the system we are discussing and analyze what is going on. So, the model that we are going to do today is going to be involved with capturing growth in a chemostat. Let me just describe a chemostat once again. This is what is called a chemostat. So, this is a tank with volume capital V. This is the volume of liquid that is present in the tank. This is stirred, and what that means, the stirring is important to define, because what it means that the constituents of the tank are well mixed. Which means that if I were to take small sections of this, if I were to analyze what are the concentrations in this cube here or in this cube here, and so on and so forth, I might take a small volumetric sample from any part of this tank. Because this is well mixed, the concentrations of all constituents of this tank are exactly the same here. And when I say that constituents of everything, all constituents have the same concentration, they would include all metabolites. So, let us say growth is taking place on glucose. So, glucose concentration is the same. Let us say acetate is a byproduct of the metabolism of the bacteria present here, and it is being secreted into the media. So, if I measure acetate concentration at different locations in this reactor, the acetate concentration is also the same. If I look at the number of bacteria present per unit volume, if I measure, in other words, if I measure the density of bacteria present at any part in this, at any location in this chemostat, that is also a constant. So, any chemical concentration or any or even the concentration of organisms in this chemostat is constant, and that is the significance of saying that this is a stirred tank reactor. In addition, what defines a chemostat is that it has an inlet and an outlet flow, a V naught, V naught. It has an inlet and outlet. Inlet has flow of fresh media. So, this is unused resources, and it is important to note that it is only media, there are no bacteria that are present in the inlet stream. So, this is just nutrients coming in, and this is happening at a rate V naught, let us say milliliters per hour. So, the units of these inlet streams are equal to volume per time. The unit of this is just the tank capacity. So, the units here is just volume. The unit here is volume per time, and this is fresh media. At the opposite end, outlet is flow out of spent media which is also happening at the rate V naught. And so, also happening at rate V naught, these two V naughts are exactly the same, which maintains the volume of the reactor at V, because at any given point in time, in every given unit of time, V naught is being added to it and V naught is being taken away from it. So, the volume of the tank remains constant at capital V. Now, since this is stirred and concentration everywhere in this reactor are exactly the same, what is being taken out is what is present in the reactor, and where in the reactor does not matter, because reactor is well mixed. So, this is whatever is present. So, bacteria are being removed, unused resources are being removed, spent metabolic waste is being removed, and so on and so forth. And this chemostat settles into an equilibrium when the rate of removal of bacteria is exactly matched by the rate of generation of bacteria because of fresh nutrients coming in. So, these fresh nutrients coming in provide resources for more growth to take place, and in a unit amount of time. So, let us say this is V naught ml per hour. So, in this 1 hour, let us say n naught number of births take place. This is the number of bacteria that are generated by division in this 1 hour. But in this 1 hour, I have also removed V naught amount of liquid from the reactor, and if this V naught amount contained n naught number of bacteria, that means that I added n naught number of individuals via growth supported by the fresh media that I added to the reactor, and this is exactly balanced by removal of n naught individuals from the reactor because of this exit stream that I have right here. So, these two balance each other out, and then the number remains constant. So, what this means here is that as a result of balance between balance between growth and exit. So, balance between growth and exit implies that number of bacteria in that tank remains constant. And it remains constant, and that is sort of the key feature. So, I hope this makes sense, and then we will be able to move forward with this. I have been using the word chemostat, tank and a reactor interchangeably. This is also called a continuous stirred tank reactor. It is continuously stirred tank reactor, CSTR, continuous stirred tank reactor, or it is also referred to as a chemostat. So, these two are used interchangeably and that should not throw you off. All right. So, let us see. Now, let us take a scenario where we have a chemostat the volume of the liquid is capital V, it has an inlet stream V naught and an outlet stream V naught. But instead of the context that we want to look at this in is that it has a species A and it has species B. And what we want to understand is that if we start this chemostat from a steady state operation. So, the total number is fixed, it is n because growth is facilitated, exactly same amount of growth take place as is removed from the exiting V naught stream. And at the start at t equal to 0 when this is started, A and B are present in steady state and in some numbers. What we want to understand is that how does the number of individuals of species A and species B change with time. So, writing this more formally, we say that at t equal to 0, Na is the, let me say that again, at t equal to 0, Na is the number of A type individuals, Nb is the number of B type individuals, and Na plus Nb is equal to capital N, which is the total number of bacteria in the chemostat. So, let me redraw that. So, we have the two species A and B, and it is a total number of bacteria in the chemostat, but N is also the carrying capacity of the chemostat. So, what this means is that we are starting at the steady state of the chemostat, where it could not possibly have any more number of individuals. It is completely occupied by A and B type bacteria that are occupying it. These numbers could be anything, and what we want to understand is that how do numbers change? How do numbers, which means Na and Nb, change with time as we move forward? And intuitively we can have some ideas about it. We know that the chemostat is being occupied by A and B, and these two species are going to have their respective growth rates. Let us say this one is growing at rate Ra, this one is growing at rate Rb. So, intuitively we can say that if Ra is greater than Rb, if this is the scenario that we are looking at, then as time moves forward, NA will increase and NB will decrease, because this is growing faster than B, which means that A is going to grow faster. Number of individuals of A type are going to go faster and B types are going to go slower. And to think a little more deeply about that, why that will happen is that imagine that they are both being replaced at the same rate. So, the chance of who goes out is the same for either A or B, but if this is replicating faster as compared to the B type, then A is adding to its number faster as compared to B. However, they are both being washed away from the reactor at the same speed. So, because of the virtue of its faster rate at which it is adding to its numbers, A is going to grow faster as compared to B. And eventually, if we let this play out for a long time, all of B types should be replaced by A type individuals, and eventually only A type will be left. Eventually only A type left. And similarly, the opposite argument works as well, that if RB is greater than RA, then as we move forward in time, B type individuals will replicate faster, they will outcompete the A type individuals, and eventually B type will take over the chemostat. On the other hand, if RA is equal to RB, both the species are growing at exactly the same rates, then the numbers, their relative frequencies should stay the same. But through this model, what we want to try and understand is build a quantitative understanding of how much time will it take for population of A to be 90% of the entire population that is present in chemostat, or how much time will it take before there are only 10 individuals of B type left in the entire reactor whose carrying capacity is, let us say, 10 to the power 11, and so on and so forth. It is this type of quantitative framework that we seek to develop. So, to do that, let's redraw the chemostat. V naught, exit at V naught, capital V, this is A and this is B. So, to develop that quantitative framework, let us take a look at this. So, for A type individuals, their number is NA, B type individuals number is NB. NA plus NB is capital N, which is also the carrying capacity of the chemostat. If that is true, then what we are going to do is we are going to define a quantity, that fraction of A type individuals. So, the fraction of A type individuals is simply going to be, let us call it x, is simply going to be NA divided by NA plus NB. But since this is a constant, so carrying capacity is constant with time, let us call it some k. So, this is just equal to NA upon k. Similarly, we have fraction of B type individuals, and let us call it y, and that is just equal to NB divided by NA plus NB, which is equal to NB upon k. And what we should note here is that x plus y exactly sums up to 1. That is always going to hold, because there is no other third type of individual present in the population. A and B is all there is, and population size always remains at the carrying capacity. So, any increase in number of A is going to come at the cost of the same amount of decrease that happens in number of B type individuals. And in this framework, instead of tracking actual numbers, we are going to track how do the fractions of these two type of individuals change with time. So, we will not develop an equation for dNA by dt. Instead, we will develop an equation for dx by dt. So, we will not do this, but instead we will develop an equation like this. So, dx by dt will be comprised of two parts. The first part is what adds more A. So, the first part is what adds more A type individuals minus what removes A type individuals. In this chemostat, the question we are trying to ask is that A type individuals are being generated by growth, and this growth is going to add to more A type individuals. However, A type individuals are also being removed from the chemostat by the exiting stream, and that is the second term that we are writing down here. So, what adds is the answer to this is just growth. So, that is easy to write, that we will just say that is RA times X. This is the growth rate associated with A, and X is a representative of how many A type individuals are already there in the chemostat. What removes A type individuals from this environment is simply the exit stream, but it is not easy to say what is it, how many A type individuals are exiting per unit given amount of time, because it is not just A type, B type individuals are also exiting. So, to estimate this quantity, we will make an assumption that rate of exit is proportional to frequency. What that means is that if A and B are present in 50-50 ratio inside the tank, then if I check this exiting stream that how many are A type and how many are B type, in the exit stream also there will be 50-50. However, if A is to B in the tank is 90:10, then in the exit stream I will also find them in a ratio 90:10. So, whatever is present inside the reactor and is well mixed is going to be seen in the exiting stream associated with this reactor, and that is not a bad assumption at all to make. So, what this tells me that exit is going to be proportional to X. The more A there is, the more of A is going to be washed away from the reactor, but this needs to be multiplied with a proportionality constant. So, exit, if I write this as what is the rate of exit of A, it is proportional to X, but I do not know what should I multiply, what is the proportionality constant. So, since I do not know that here, I will say rate of exit of A is simply equal to phi times X. So, I will just multiply this by phi and leave it at that, where phi is some proportionality constant which I do not know, which as yet I do not know. So, that gives me the first equation that I have to work with, and hopefully this makes sense. So, similarly, so let us rewrite the first equation again. We have dx by dt equals Rax minus phi times x. Similarly, we have the other equation for species B, which we can write as dy by dt equals Rb times y minus phi times y. Now remember, phi is a proportionality constant that I know it exists, but I do not know what it is. What we are going to do is sort of a mathematical trick here, is that we are going to add these two equations. Add the two equations. And what this tells me, the left hand side becomes dx by dt plus dy by dt equals Ra times x plus Rb times y minus phi times x plus y. And now we have to understand each of these three terms and what they actually represent. First, let us start with the easiest one, that x plus y. Remember, what is x? X is just the fraction of x, fraction of A type individuals. Y is just fraction of B type individuals, and both these fractions when added up is simply equal to 1, because there is no other type of individual in the reactor. So, x plus y can be simply removed and we just have 1. Phi is something that we do not know, so we will leave it at that. Let us move to the left hand side. Let us see what each of these two terms means. Dx by dt means how is x changing with time, and dy by dt means how is y changing with time. But remember, we started with this assumption that this chemostat is operating at its steady state, which means that if I have A and B type of individuals and let us say they are at 50-50 ratio, then as we move forward these ratios will change, but they will always add up to 1. So, if there is an increase in A type individual, it has to be matched by a decrease of the same quantity in the B type individuals, or if B type individuals increase, that has to be matched by the exact same decrease in the A type individuals. So, these two are not independent with each other. In fact, if x is increasing, y is decreasing at same rate, which means if this is positive, this is the exact opposite, that is of the same magnitude but negative, or if x is decreasing, y is increasing at same rate. What that means is, so let us say if dx by dt is increasing at 0.04 per time, if dx by dt is positive and is this value, what that implies is that dy by dt is simply equal to minus 0.04. Add them together and we get 0, and so on and so forth. So, these two quantities actually, because of the setup that we have, when we add them together is equal to 0. So, what we get is phi is equal to Ra times x plus Rb times y. And now we come to this middle term and try and understand what this is. And this, you should realize, is the mean fitness or mean growth rate of the population. What that means, if species A is growing at, let's make a table to understand this better. Let's say this is Ra, let's say this is R. So, for A, let's say Ra rate of growth rate of A is let's say 0.4 and growth rate of B is let's say 0.6. Then if any given point in time x is equal to 0.5 and y is equal to 0.5, which means the number of A type individuals is 50%, number of B type individuals is 50%, then the mean growth rate is simply equal to what is the growth rate of A, which is 0.4, times how many A type individuals are there in the population, which is 0.5, plus what is the growth rate of B, which is 0.6, times how many B type individuals are there, which is 0.5. So, this comes out to 0.2 plus 0.3, which is 0.5, which is the exact mean of these two because the population numbers were 50-50. If however later on x becomes 0.1 and y becomes 0.9, then phi becomes RA is 0.4 into 0.1 plus RB is 0.6 into 0.9. This equals 0.04 plus 0.54, which is 0.58. So, now because of the change in the fraction of individuals of each kind in the population, the mean growth rate has increased to much closer to what the growth rate of pure B is. And we will see some of the implications of this in the next video, and we will continue further.